Cool. So we've been talking about maps from schemes to projective space. And of course, one question that's sort of come up naturally is maybe if I change the base here, right? If X is a scheme over spec A, then I get a map into projective space over Pn of A. And I might ask, when is this an inclusion? And I should say closed. A closely related question is, when is X equal to proj of S or some S? Now, these are not quite the same because S might not be generated in degree 1. Then that's basically equivalent to this, right? So if S is generated in degree 1, there's a surjective map from this polynomial ring to S, right? And that induces a map from proj of S into En of A as a closed embedding. All right, it's closed embedding because this is a surjective map of rings. All right, so these are two closely related but not quite the same concepts. And of course, now that we know that maps to projective space are about line bundles, we can refine this question a little bit. We can say, for a given line bundle L, when do I know this is getting, for a given L, let me just put a question mark over this closed inclusion, such that L is equal to whole back of O of 1. Right? So given a line bundle, I can not just ask, well, do I have an embedding of X into Pn, but do I have an embedding of X into Pn which comes from sections of this line? All right, and similarly, I can ask, when is X equal to proj of some ring or some S such that L is isomorphic to O of 1? So I can think about this not just as kind of an abstract question of X is X proj of something, but is X proj of something, and is that isomorphism induced by a particular line bundle? All right, so when these things happen, there are specific names for the resulting line bundles. Let me call this A and this B. So when A holds, we call L very ample. And since this base ring is making an appearance here, I'm looking at the projective space over A. It's also showing up in here. That's sort of part of the story, that it's over the space. And we call L, and when B holds, we call ample. Yeah. There's a little bit of trickiness about bases here, right? Because in order to make this ample over A, I should say S and A and A algebra with S0 equals A. Yeah. So as this is discussed in Vacchial, there's sort of a relative notion of ample, and there's also an absolute notion of ample, whereas very ample only makes sense relatively. Okay, cool. So, I mean, of course, we could just say, all right, we had some property that seemed kind of interesting. We gave that property a name because it happens reasonably often. It's sort of a question I'm interested in. So maybe we should talk about an example or two. So on Pn, well, every line bundle we saw is of the form O of K. And in this case, it's very ample if and only if it's ample if and only if K is positive. Right? So if K is positive, I get this K upal embedding of Pn maps into, let me get this right, n plus 1 plus K, choose K minus 1. And why is this here? Because this is the number of monomials of degree K in n plus 1 variables. So if you think about this map as actually being coordinates, I have my x0 up through xn. And what this maps to is the coordinates in here are every monomial of degree k in all n plus 1 variables applied to these guys. So the first one of these is x0 to the k, and then x0 to the k minus 1, and x1, etc. N plus k, choose k. I mean, if I were doing this with stars and bars, I would have n plus 1 stars, but I would have k minus 1 bars. All right, anyways. Yeah, well, the usual way to get this right is to, think about some small case and try to get it right in that case. Like if n is 2, then I want to be getting k plus 1 variables here. So hopefully I did that right. I think I want a minus 1. Oh, no, if n is 1. Okay, great. Yeah, perfect. All right, cool. On the other hand, right, if L is trivial, let me just include this for completeness, right? We discussed whenever you have a line bundle, you can first look, is it base point free? So you can look at complete linear series. That means look at all sections of the line bundle and try to use those to define a map to projective space. When that's going to happen is when the series is base point free, which is when at every point, the stalk of the line bundle is generated by global section. So this is actually something that comes up reasonably often. We say that a coherent sheaf F is globally generated if the sections of F over the whole space, when I map those to the stalk at a given point, generate over the local ring at that point. For a line bundle, a line bundle is globally generated, which is the same as saying it's complete linear series is base point free. If for all P, there exists S, a section of this line bundle, such that P is not in the vanishing set of S. So a point which was in all of these vanishing sets would be, by definition, a base point of this complete linear series. That's what base point is. Okay, so all of these guys are base point free because at every point, there's at least one coordinate that doesn't vanish, and I can take the kth power of that coordinate. This guy is base point free because there's the constant functions. It can take a non-zero constant. That shows that every point is not a base point. What being base point free tells you is that you get a map to projective space. But in this case, right here, I'm getting this map to projective space in this dimension. In this case, I have a one-dimensional space of sections. So I can't take any ratios. So I get the map from Pn to P0, which is a point. Or if I'm doing this over Z, it's actually spec of Z. But more generally, if I put A here, it would be spec of A. All right, so this sort of smashes out all the projective stuff. Yes. So this means that if I look at the stalk at a point, right, the stalks of global sections generate that stalk, right? So all of these guys are globally generated because there's at least one global section that has non-zero stalk at every point, right? I should say that in the opposite order. At every point, there is a global section whose stalk there is not zero, right? For these guys, I have to choose different stalks for different points, but there always is one section, which at any given point, there's at least one section that has non-zero stalk there, or not just non-zero, non-vanishing, not contained in the maximal ideal times this guy. Those aren't global sections. So if I take O of K for K negative, I was just getting there, this has no non-zero global sections. So obviously, it's not globally generated. Right? So I always get a map on the base point free locus, but in this case, all global sections are zero. Every point is a base point, and so I get nothing. If I have at least at least one non-zero section, I always get a rational map, at least. But this map to projective space is given by ratios between sections. So I have to have at least two sections in order to get a map to P1. That's sort of non-trivial. Otherwise, I'll just get a map to P0. Okay, cool. So it wouldn't be all that useful to define these words. I mean, still sometimes be useful, but not really that useful. If we didn't have some other characterizations of them, some other way to think about them. So in particular, ample has two other very important ways to think about it. So here assume that X mapping to spec A is proper. And I'll just mention again, I'm still assuming that everything is Noetherian. It actually won't matter that much because most of the sort of dumb non-Noetherian stuff you can do, you can't if you're proper. So in particular, being proper implies that you're quasi-compact, even if you're not Noetherian. A line bundle, and I'll just note we haven't proven this, but the fact that this is proper shows that sections of any line bundle on X is finitely generated over A. That's a non-trivial theorem about proper maps. So you should just imagine whenever I take sections of a line bundle that it's actually finitely generated over A. Line bundle L is ample. So that means it gives me a way of realizing spec as proj of something, but maybe not generated in degree 1. If and only if, I'm going to use the letters from Vacchiel, but I'm not going to do this in quite the generality that Vacchiel does. Some power of n is very ample. And all of these are sort of variations on them where you can make them a little large, stronger, a little weaker. So you can make this stronger by saying for some lower bound, for all n above that upper bound, this power is very ample. D, for all coherent sheaves, if on X the tensor of F with a power of L is globally generated for n sufficiently large. So whenever I write the two greater thans, that means there's some lower bound such that for all n greater than that, I get this property. And C, X as a cover by affines of the form XF. So this is X minus the vanishing set of F. And I need to add something important here, where F is a section of a power of F. So ample things is always about powers because I'm looking at proj of S, right? And proj of S sees all degrees. Maybe actually a sort of side note before we start discussing this. if you're interested in this question of is L proj of some ring, if you've chosen the line bundle, then there's an obvious candidate. So given X and L, let S sub XL be the sum over all non-negative integers n of the sections of the tensor powers of L. So this is a graded ring. This is the part of degree n. All right, so this is sort of the natural ring that you would hope that X is proj of. So L is ample if and only if X is proj of this ring. Yeah. Yes. Right. So the way you should think about this is if I secretly know that this is the case, right, then proj is explicitly constructed by taking sections of these powers, homogeneous elements of positive degree, and looking at their non-zero locus, inverting them, right? So when you make a proj, by construction, inverting that guy gives you something alpha. So again, there are kind of lots of versions of this where you can make this a little bit stronger, a little bit weaker, which can be beneficial depending on which way you're trying to apply the theorem, right? If you are trying to show something is ample, you want as weak a statement as possible, right? In fact, if you are ample, every subset of this form will be affine. But if you're trying to prove that something's ample, you don't want to have to worry about doing that. In fact, it's enough to show that there's enough of them to cover X. All right. Similarly, you can relatively easily show that showing that one power is very ample actually implies that all sufficiently large powers are very ample. And if you know that your line bundle is ample, it's more helpful to know that all sufficiently large powers are very ample. But if you're trying to show that it's ample, it's useful to know that you only need to do one power. Yeah.
So why is like F tensor out to the end?
What's F to the? I mean, what would be the map? Right? I mean, think about modules, right? You would never suggest that A tensor B to its nth tensor power is the same as n A to the nth tensor power, right? I mean, I think another answer to that is, right, this is not necessarily a line bundle. This is something of rank m or, potentially higher rank. This tensor product has the same rank. This is the same bundle. Another answer to that question is, so once you've gotten this far, there's a natural generalization of this, right? We know that coherent sheaves on X come from graded modules over proj. So how do I naturally define a graded module that I hope is going to give me F? Well, I can define M sub F L to be the sum over non-negative n, or I don't even need non-negative n, of sections over X of F tensor L to the n, right? So why am I tensoring with powers of L? Because my ring is sections of powers of L. And so if I want a module over this ring, I have to be able to take a section of F and multiply it by a section of L to the n. And then what do I get? I get a section of F tensor L to the n. So this is a graded module. And I should say you can prove that these operations are left adjoint to the operations of sort of sheafify. I mean, actually, I shouldn't put only positive n here. I can put all n, but we also know that the degrees, negative degree guys, don't affect the sheafification at all. All right, and so this globally generated hypothesis, that's essentially saying that if you take this module and then rebuild the sheaf from it, you'll succeed. You'll get the whole sheaf. All right. Yes. Yes. And as I say, if you look in Vakiel, he has A and A prime, he has C, C prime, and C double prime. And it's also maybe a tiny bit easier to kind of structure the proof if you look at all these different versions of it. But I think I'm not going to try to do kind of the proof in full generality. But maybe we'll sort of discuss some of the ideas of why you should expect this to be true. So important notes. If L is very ample, of course, that implies that L is base point free. And L, very ample tensor. L prime, which is base point free, gives me this guy, which is very ample. And the proof here is this guy gives me a map from X into Pn, which is a closed embedding. This guy gives me some map of X to Pm, which might be a closed embedding, might not. This tensor product gives me the natural induced map into the product, followed by the Segre embedding. And the fact that one of these factors is a closed embedding implies that this is a closed embedding. Note, this is enough to tell you why you get globally why you could require that every sufficiently large power is very ample, because if you sort of play with this a little bit, you can get a big enough power where everything is a very ample line bundle tensored with a base point free one. Cool. All right. So now let's talk about why we get some of these equivalences. So for example, if A holds, well, that implies that I can write X as Raj of the sum of some S, where I can identify S1, the degree 1 things, with the sections of this very ample power of FV. All right, but we know that, so this is even sort of an embedding of X in DNA. Well, we know a bunch of affine open subsets of Pn, the open subsets where you require one of the coordinates to be non-zero. So if we take F1 up through Fn to be a basis of the sections of this nth power, the very ample one, then xf1 or xfi is affine because it's a closed subset of the affine subset of Pn, where the ith coordinate doesn't vanish. And these cover X. All right, so this tells me why A implies C. Why does C imply B? So if I look at the sections of F on this affine open cover, then that gives me some module M, I'll put parentheses F here. Since XF is affine, it's globally generated. The restriction of F here is globally generated. By some sections, M1 up through NM of F. So these are in sections of F on here. By the QCQS lemma, this is the same as taking the global sections of F and localizing at F. I got that right. I'm going to be a little bit careful here. Oh, right. No, that's the wrong way to think about this. Sorry. And the reason is because remember here, F isn't a section, isn't a function, it's a section of this line bundle. Okay, so let me not try to state too explicitly why this is so, but by the QCQS lemma, we can write each of these guys as some ni of F divided by F raised to some power, where now, what sort of thing is this, right? So I'm dividing by a power of this line bundle. So here, my ni has to be n. F tensor the line bundle to the n ai. So this is why you're sort of getting something about, not about F, but about its tensor product with this line bundle. Because what I'm inverting is a section of a power of the line bundle. Okay. Again, I'm probably, yeah, really short on time. So let me just say you use the usual trickery of saying, oh, I could replace F with a power and replace this guy with a thing to make all of these guys be sections of the same power of the line bundle. And then, oh, I only have finitely many affines because I'm quasi-compact. So I only need to do this finitely many times. So there's some power of the line bundle where I get global generation. All right, and let me just not worry about the last implication. We're running low on time. There's other stuff I want to cover today. So if you want to read why D implies A, you can go read it in Verkeel. So sort of the important notion of what the important thing this tells you is that being affine, it has to do with having inverting sections of your line bundle and getting lots of affine open sets. Right? And we know that's something that happens with a proj, and it turns out that's the only condition you need to get a proj. Note, there exists a relative notion. I could have X mapping to some Y by some map pi, and then have a line bundle on X is pi ample or pi very ample if this holds for an open affine cover of Y. So we've covered what it means when Y is affine over there. And now I'm just saying, okay, well, I have a line bundle. If I want it to be ample or very ample, I just need to require that locally on the target. And this is really the right notion of being a projective map. Is one with an ample line bundle. And one of the things that I think we're just going to have to skip for time is that there's a notion of relative proj. Right? So I could look at this line bundle on X, look at its powers, and push those forward to Y. And I would get a graded algebra of coherent sheaves on Y. And there's a notion of proj of that. And one way to say what it means for L to be ample is that X is proj of that graded algebra of coherent sheaves on Y. Similarly, you can define relative spec, which is a nice way of defining affine maps. The map is affine if it's relative spec of a algebra in the category of coherent sheaves on the target. Okay, cool. So now let's try to cover a few examples in the limited time we have left. So yeah, maybe this is the only example we'll have time for. We'll talk about curves another time. Let's talk about the Grassmannian. So informally, the Grassmannian, you've probably encountered, hopefully encountered this in some smooth context. Gur Kn. This is the moduli space rank K quotients a free thing of rank K. So the quotients here is probably slightly different from the context in which you've seen this. If you've seen the Grassmannian defined before, most likely you saw it as the space of k-dimensional subspaces of an n-dimensional space, either over R or over C. Of course, it's equivalent to say quotients, and that will sort of work better in general. So how do I turn this into an algebraic geometry definition? Well, we know that schemes are characterized by saying what Hom of another scheme into them is as a functor from schemes to sets. So what is Hom into the Grassmannian? Well, we kind of already know because we know what the answer is for projective spaces. So Hom into a projective space means I have a line bundle and I have n+1 sections which generate that line bundle. And well, my n gets a little bit off here, but that's okay. So Hom into here is do a locally free sheaf on X and S1 up through Sn, which generate Q. These are going to be sections on X. There's a sort of slightly nicer way to think about this, which is I can think of these n sections as giving me a map from OX, take direct sum n times to Q, and I'm requiring that this map be surjective. Right, so I can think of these n sections as n maps from O of X to Q. I can take the direct sum of those to think of that as one map from this free sheaf to this guy. And those guys generating means that this is surjective. Okay. Of course, if I look at the points of the Grassmannian over a field, I get the usual definition of the Grassmannian. So if I look at the points Gur K N of F, I get dimension K quotients F to the N. Locally free on spec of F just means a vector space. Doesn't, sorry, of rank K. So, yeah, sorry, that's pretty important, of rank K. But for example, if K is equal to 1, if I look at Gur 1, n+1, that's Pn. That's something we've proven, that maps of X into Pn are line bundles with choices of n+1 sections that generate the line bundle. They give me a surjective map from the free thing to my line. All right. So theorem I've just told you this functored points. I haven't even proven that there's a scheme here, but there is. And in fact, it's projective. Do I have any time to prove this? No, I do not. So very, very quick sketch of the proof. How do we see this? I mean, how do we see that this guy is a scheme at all? So we find an open cover where we can understand better what's going on. So given I of size k in integers from 1 up to n, let ger sub I, so this is going to be an open subset of the Grassmannian, and it's the open subset where the SIs for I and I generate Q. So because Q is rank K, that means that if I look at the subbundle OK, or I should say O of I, so the sum end where I only use the coordinates in I, mapping to Q, that's an isomorphism. If this condition is satisfied, Q is trivial, and it's trivialized by the map from the coordinates in this set I. Well, if that happens, what other choices do I have? So this map is automatically going to be surjective. So on ger I, taking O of n and mapping that to Q, well, I can use the isomorphism from the subspace where I only use the coordinates of I to Q. And so what other information do I need? I need how the other coordinates map there. So it's equivalent to sum from O of this guy minus I to O of I. I'm just choosing those guys. So it's equivalent to choosing an n minus k by k matrix. So actually, ger of I is isomorphic to this affine space. And this is, again, if you have looked at the Grassmannian before, you might have seen this sort of set of charts on the Grassmannian where you choose, and since I'm thinking of it as a quotient, it's I choose which unit vectors are going to give me a basis after projection. And then I just get to choose randomly where all the other unit vectors go. Okay. And oh, yeah, we're out of time. So this open cover by schemes shows me that this is the scheme. It's glued together from finitely many copies of affine space, where the inclusion I can sort of figure out from what happens when I lie in both of these. So let me just say, why is it projective? So in order to show that this is projective, I should find a line bundle that this is the non-vanishing set of a bunch of sections. So on ger, there exists Q a rank K tautological bundle. And if I take the kth wedge power of this guy, so this is the bundle whose fiber at each point is the quotient itself. I can sort of glue it together by looking at this affine space and thinking of this guy as a bundle on the affine space. So this is a natural way of cooking up a line bundle. And there's a natural map from the kth wedge power of the trivial bundle to this guy, which is given by wedging together the sections that lie in. So this is a section of this line bundle, and this is the open set where the section of this line bundle doesn't vanish. So I found an open cover defined by pulling out the zero sets of sections of this line bundle, and these guys are all affine. So that shows me why this is an ample. All right, we are way out of time, so I will quit there, and we will talk about other stuff next time. Now the quotient has dimension k, the sub has dimension n minus k. It doesn't matter, this is backwards from the usual convention, but I mean, the Grassmannian of k-planes is isomorphic to the Grassmannian of n minus k-planes, right? Like you can, the trivial bundle is self-dual. So if you really are determined to have a dimension k sub-bundle, you take the you look at the kernel and then you look at the perp of the kernel. I mean, look at the sub-bundle where the coordinates along I are set to 0.